So let's start with something called the maximum power transfer theorem, and for this we will go with something which is called a mixed grouping of cells, people. So what happens here is sometimes we use a mixed grouping of cells of identical cells actually. So I should say mixed grouping of identical cells. And this is a very special case, so you should not think that it is applicable everywhere. Only when you have identical cells, it will be applicable. So there are n cells in total, big N cells in all, which will be arranged in m rows and n columns. Right, so you will have n cells in one row, this, and you have got this, then you have got the second one, this is the second one, then you have got the third one, this is the third one, and you have got the fourth one, and you have got the R also. So like this you have got n cells. So there are n cells in a row, and like this you have m columns. So let me just copy this guy and keep on pasting it m times actually, but then I won't be doing it so many times. So I will be just saying that this one repeats m times, right, and so on. So there are n cells in a row and m such rows. So there are m such rows, m rows, and this combination is called a mixed grouping of cells, right? So this is what makes up a mixed grouping of cells. And what we are doing is we are joining all the left hand sides with one wire, conducting wire, like this, and we will join all the right hand sides here, wherever that is, with one conducting wire, like this, and across that wire we will take the output. So we will have a point A on the left end here somewhere, and a point B on the right end somewhere here, and these A and B points will form the terminals of that net battery that we have, right? And let me just make this smaller so that I can fit in more on the same page, right? So you have got an arrangement like this, and to this arrangement what I will do is I will attach an external resistance, R external. So let me just say R for that, R. And our job is in fact to figure out what should be the condition that the current in this R is maximum, right? So what I want to do is I want to find the condition that allows R to have maximum current from, in fact I should say extract, not have. I think extract is a much better word. R can extract maximum current, so extract. So find the condition that allows R to extract maximum current from a given number of cells, of identical cells really. That's because when the number of cells is fixed, then the only thing that can vary is m and n. And the question that we are trying to ask is, can we vary m and n in such a manner that allows this R to have maximum value of current? Because if the current is maximum, if I is maximum, then I square R is also going to be maximum, and then we will say that in the external circuit we are getting maximum amount of power from this grouping of cells. We would like this entire circuit of n cells in a row and m rows to act like one single battery. So what we are going to do is we are going to say that this entire circuit is equivalent to some E net with some R net and an external resistor R. And we want to figure out what is this E net, what is this R net, and then we want to figure out the value of current in the circuit, and then we want to solve for it. And then we want to maximize that current really. So in order to find out E net, please keep in mind that let's first solve for a row. Now in a row, you see that all the internal R's, all these small R's, are in series. So in a single row, and I'm doing it here down, in a single row, all internal resistances are in series. That's one. And you will see that all the EMFs are helping out each other. So all the EMFs have been arranged in a row in which all of them are facing in the same direction. So what will happen is, if you try to figure out the increase in voltage as you go from maybe the right end towards the left end, you will see that across each one there will be an increase, and the increase will be equal for each. So you can say that a single row will act as a single row will act as a cell of EMF NE and internal resistance NR. This is what each row behaves as. So this is one single row, and there are m such rows. Let's say there are m such rows, and what will happen with those m rows? You know that in each of those m rows we will have the same kind of arrangement. So there will be a cell of EMF NE, and it will be facing leftwards. There will be one R here whose value will be NR. Right, so we will have the internal resistance of the cell, of that equivalent cell in each row, equal to NR. And there are m such rows, and we need to find out the equivalent of all those m rows. So what we are going to do is, we are going to use that law that we know. There are m such rows, people. How do we proceed in such questions? We first figure out the net internal resistance of the net cell. Right, so whatever net cell we are thinking about. So let's say I want to imagine that this m row system gives me a net EMF that is facing leftwards like this, E net, and that has got an internal resistance equal to R net. This is what I get finally, is what I'm claiming. I can figure out the value of R net very easily, because R net is this NR, this NR, this NR, and all those NRs attached in parallel. So therefore R net becomes NR divided by M. Right, so this is the value of net internal resistance of that net cell that I should attach there in the circuit. And then finding out E net is actually pretty simple. I will use that formula, E net by R net. So let me use that here. And how we use that is E net by R net is equal to E1, so NE by R1, so E1 by R1 plus E2 by R2 plus E3 by R3 plus, and I will have m such terms, one term for each row. So m terms, and you will see that each term will be just equal to E by R. So on the right hand side I'm going to get ME by R, and that's E net by R net. But I can find out E net from here very easily, and E net is equal to M E by R times R net, and R net will go there in multiplication, and R net is NR by small m. So I'm going to get NR by small m, and some terms will cancel out, specifically m goes off and small r goes off, and you will end up with N times E. So the EMF in a single branch, in a single row, that itself will be the net EMF as expected. So our expectations were also that. And so now what I can say is I can approximate this entire circuit as a net cell of EMF NE and of internal resistance equal to NR divided by N. So what I have got is a circuit like this, people. I have got a cell internal resistance this is n times e, this is n r by m, and then I've got an external resistor here, and I want to figure out what is the value of I, or the current flowing in this circuit. And that's very easy to find out. I'm doing it here on the right hand side. I is equal to NE divided by R plus NR by M. Take LCM, and that will look like NME by MR plus NR, and which is equal to NE, because M into small n into small m will give you big N. So NE by MR plus NR. And you see that the numerator is a constant, and so we are interested in only the denominator. And for I to be maximum, we should have the least value of the denominator. So for I to be maximum, denominator should be minimum. And then this problem can be solved in two different ways. There is the usual method of finding out the derivative and so on. So what I want is, I want a function of m and n, which is mr plus nr, to be minimum for fixed values of big R and small r. So I can treat small r and big R as constants, and because it's a function involving two variables and we have no clue how to perform minimization of a function of two variables, we will have to somehow convert this into a form where it is a function of only one variable. So we can use this property, and mn is equal to big N. So you can say m is probably big N by small n. And what you can now say is that the function that you want to minimize is only a function of small n, which is n by small n times big R plus nr. And you can go this way, right? You can, so since now this is a function of small n only, if you want to minimize this function, d by d small n of this function should be equated to 0. You figure out the value of small n from there, and then you will be able to get some answers. But then that's not a very efficient way of doing this entire problem, people. There is a much better algebraic method. So of course we can go via this method, and I encourage you to actually do this and get the answer via this method also. But then let us go for an algebraic way to solve this particular problem, and it's very interesting because I don't know whether you have seen it or not, but what we can do with the denominator here is, so I've got an algebraic method. We have to find the least value of m times big R plus n times small r, and you rewrite this function as mr plus nr is equal to root of mr plus root of nr whole square. You can write this minus, so you will get an extra term that will be 2 times root of mn big R small r, or you can write the same function as probably this orange one, which I'm going to write here, root of mr minus root of nr whole square, and I'm going to get one extra term, and so I will have to add 2 root of mnrr to throw it off, right? So I can write this equivalently in two different ways. And remember that when I want to find out the least value of this function, the one that I want to do this is in this orange way, right? So I want to write this mr plus nr in the way in which I have expressed the orange in expression here. That's because now I know the least value of this square. I know that there is this number that has to be added, and this number has to be added to a square term, and square terms are always greater than or equal to 0. So the value of mr plus nr will always be, so therefore the value of mr plus nr will always be greater than or equal to 2 root of mnrr, where the equality holds where the equality holds only if the square term becomes 0. And if the square term becomes 0, then I am saying that root of mr is equal to root of nr, or I can equivalently say mr is equal to nr, or I can say big R is equal to nr by m. But that's a wonderful expression, and I will show you why. Because we would have seen something earlier we would have seen something earlier is actually associated with this term nr by m. Let's go up and look here. Nr by m is here. So nr by m is the net resistance of that equivalent battery, right? It is the net R of that equivalent battery which we have put here in the circuit. So now we get the condition. We say that current will be maximum in the external resistor due to a mixed grouping of identical cells if the net internal resistance equals the external resistance. So please keep this in mind. Please keep this fact in mind, and let me just change maybe the color of few terms here. This much. And maybe this much. Yeah. So there you go. So please keep this in mind, and this is called the maximum power transfer theorem.